Three major types of aqueous reactions are follows. They are and how they relate to net ionic equations. They are precipitation, also known as salt metathesis. Salt metathesis, the formation of salt. There is acid base, and there is redox, or oxidation reduction. The basic premise here is that these are reactions that happen within aqueous situations. Salt metathesis is when is a double displacement where we have two aqueous scenarios. So I'm going to use the abundantly clear one: silver, nitrate, aqueous, and like say, we'll say sodium iodide. We'll mix it up: sodium iodide, aqueous, and aqueous, and sodium iodide and aqueous form a solid, silver iodide, and an aqueous solution, so sodium nitrate. The big idea is two aqueous come together to form a solid. Acid base, we have some sort of acid containing compound. Acid, right now, as we know it, is a hydrogen donor. Nitric acid is a good example. So would hydrochloric acid. So would sulfuric acid, or hydroiodic acid, or hydrobromic acid. There's many different acids, but the idea is that H plus NO3 or H plus some other compound that's going to make it lose the H. Then we have a base. Typically, it's going to be some sort of hydroxide. Now, there's other bases that we can worry about, but these are the most common ones. The idea is that an acid and a base come together. They typically form water, which is our liquid, and a salt. That's also a double displacement type of reaction. See, we swap places from the cation to anion pairs. We form HOH, which is water. The big idea is that we go from two aqueous to a different state of matter, whether it's liquid or solid. Now, in a redox reaction, it could be many different ways. The redox is going to be almost entirely different in that we see a change in charge. This could be a single displacement, like this. We could have, say, copper oxide and iron solid. Both these are solids. Going to iron oxide and copper solid. This would be a single displacement. But the idea here is that this iron is charged 0. This copper is charged 0. But the iron within this compound is 2+, and the copper within this compound is 2+. Now, those are really easy to tell whether this is a redox because we have a pure element. But you could also have something crazy like an aqueous one. This guy is 3+. This guy is 2+. This guy is 1+. This guy is 2+. If we break it down, all these guys are aqueous. But the main thing happens is we change charges. Copper goes from 1 to 2. Iron goes from 3 to 2. Copper goes up by 1. Iron goes down by 1. One of the big things here is in a net ionic equation, anything aqueous gets broken apart. Anything aqueous gets broken apart, and things that are aqueous and what are called spectator ions get canceled out. In the case of silver nitrate, we break that down into silver nitrate. Silver plus, nitrate minus, Na plus, and iodide minus goes to silver iodide solid. Solids don't break apart in a net ionic equation. And then we have Na plus and NO3 minus. So what do we see? Na plus, Na plus. These guys can be canceled out. NO3 minus, NO3 minus. The net ionic equation becomes silver plus, iodide minus becomes silver iodide solid. That is what it means to be a net ionic equation. We've broken it down and simplified this as best we can to show us what action is being taken. Let's go to the acid base. H plus and NO3 minus. Li plus and OH minus goes to H2O. Pure water doesn't get broken apart. Only the aqueous gets broken apart. So H plus, water, not the same. But NO3 minus and NO3 minus are the same and can be canceled out. Li plus and Li plus can be canceled out. But OH minus is different from water, and it cannot be canceled out. So the big reaction on an acid base is H plus and OH minus goes to water. And while I cannot simplify that one any because they're all solids, I can simplify this guy. Copper plus 1 and nitrate minus 1 goes to an iron 3 plus and 3Cl minus goes to Fe2 plus and Cl and 2Cl minus and Cu2 plus and NO3 minus, and I ran out of room. Let's zoom this out, sorry. And Cl minus. Nitrate, nitrate. Cu plus 1 and Cu plus 2 are different. They would not cancel out. 2 chloride, 3 chloride cancels out with 3 chloride. So in this oxidation reaction that occurs within aqueous chemistry, copper 1 and iron 3, an electron is lost by copper and goes to iron. Electron is being transferred from copper to iron to make them swap, to have the charges change. In a net ionic equation, only the driving force is really shown. Everything else that is not important kind of falls away. And that's the case with aqueous chemistry. So we drew that and we simplify that. But that is a lot of the aqueous chemistry. To remember, quick rules of solubility. Quick rules of solubility. I can't give you everything, but nitrate and acetate, C2H3O2, are always soluble. Soluble. And then lithium, sodium, Potassium, rubidium, cesium, and ammonia are always soluble. These guys are always soluble. So if you have any of these guys with a cation or anion, they will always be soluble. Everything else is suspect. Everything else can be suspect. But big cases, CO3 2 minus is usually not soluble. S2 minus is usually not soluble. I'm trying to remember any of the other big ones, but I think those are, I think OH minus is usually not soluble. So, except when with these rules. Maybe phosphate. I don't want to be giving you too much faulty information, so, but usually not. Some of the other stuff you will have to get. There are rules you can look up, but just a quick thing. If you know these rules, you can immediately eliminate some salts. You can immediately eliminate some salts because typically they get used. In the case, we said silver nitrate. That's soluble. Lithium hydroxide. That was soluble. HNO3. That was 100% soluble. HNO3. So whenever you see those guys, we can treat them as always being soluble all the time.